So today we're going to talk about variation. Now, freshman year we did a little bit of this discussion with direct variation, or we also call it directly proportional type problems. Problem states y varies directly with x, has an equation that looks like y equals kx, where k is a constant, and what was true about all direct variation problems is if you were to graph them, they all go through the origin, number one, because that looks like the equation of a line whose y-intercept is 0, and they made a line. X ends up being the variable, y is a variable, this constant k actually acts like the slope. We're going to add a couple more variations today. One is inverse variation, and in inverse variation they also call it inversely proportional. They'll say once again y varies inversely with x, and I like expressing it as xy is equal to k, where k is the constant. You'll also see it written as y equals k over x. They just divide x on both sides. This graph is a little bit different. It looks like some of the rational functions we've been graphing, mainly because if we rewrite the equation we get a rational function. There's an asymptote both at the vertical and horizontal region, and we get a curved graph. Inversely proportional means as one thing goes up, the other goes down, while direct variation means as one thing goes up, the other typically goes up. Finally, we have something called a joint variation, where it's known as a direct variation with a product of two quantities. So you'll see y varies jointly as or with kx, and here's the direct variation, y equals k, and then there's my product of x and w, where k is still a constant. Typically you don't see a lot of graphs of that, but it's just kind of an idea. And then later in the lesson today we will combine a couple of different variations into a singular variation known as a combined variation, but there's so many combinations we don't state it in an equation form. So let's go ahead and do a couple of problems. It says z varies directly with the cube of y. So if I wanted to take and write the equation of that, I'd say z, and I need a direct variation, so that's k times that next term, and this next term is the cube of y, so I say y cubed. And we want to find the constant of variation, so that's k in this case. They give us values of z, which is 20, unknown of k, and y is equal to 1.5, but we're going to cube that. So then we divide both sides by 1.5 cubed, and let's just approximate this answer to about 5.93. Now in this case you got the period of a pendulum, we'll call P for a period, varying directly, so that's k times something, with the square root of the length. So the square root, we'll call that L. If the pendulum length is 64 and the period is 1.6, what's the period of a pendulum with a length of 1? So in this case, they're giving us two situations. Here's 1 in the singular underline, and 2 with an unknown second piece of that. Now what I typically do on this, I know if y equals kx, and k is a constant in every single case, and I'm given two situations, so 1 and 2, oops, sorry, 1 and 1 for the first situation, and 2 and 2 for the second situation. I know that if I was to divide here, y1 over x1, that's equal to k, and then I have y2 over x2, that's also equal to k. So doesn't then y1 over x1 equal y2 over x2? And that's why they call it directly proportional, because now I have a proportion. I like setting anything up that has two situations in a proportional case. So in this case I have a length of the pendulum of 64 centimeters, I'm going to put that in my denominator. And I have a period of 1.6. And that's my first case. Then I have case 2, where I have a length of 1 meter. Now here's the problem. This is in centimeters, this is in meters. I'm going to need to use either centimeters or meters, and since I've already written my centimeters down, I know 1 meter is 100 centimeters, so I'll put that in the denominator, and I want to find the new period, or call it x. So now I have to do a cross product. I know this multiplies to 10, so I have 1.6 times 10 is equal to 8x. I know that 16 is equal to 8x, and x equals 2 seconds. Problem done. So now we have the volume of a sphere varies directly, so volume equals k with the cube of its diameter, d cubed, and it says the volume is 288 pi when the diameter is 12 centimeters, and we want to find the variation constant again. So this is 288 pi is equal to k times 12 cubed, and again we're just going to take and divide. We end up with 288 pi over 1728, and that's equal to k. This actually reduces to 1 here and 6 here, so I have pi over 6 is equal to k. So now we've got an inverse variation problem, and it says y varies inversely as the square root of x. Again, I like writing this as xy equals k. You'll notice in this case it's a two-case situation. Here's my first case, my second case here, but I have my unknown of y. And again, you'll notice that if I have case 1 of x1, y1 equaling k, and k is also equal to x2, y2, I can set these two quantities equal. Notice it's not proportional necessarily, but if I was to take and divide the y's on either side, you'd notice x1 over y2 is equal to x2 over y1. They call that inversely proportional. I'm not a big fan of writing the inverse proportion because I find people mess that up all the time. I'd rather use this notation. So in this case, I have my first x of 12, my first y of 40, and that would equal my second x of 15 and my second y being unknown. Now I just plug it into my calculator, and I have 12 times 40 over 15 is equal to y, which is 32. And that gets me done. So a little more reading on this problem. It says the electrical resistance of the wire varies directly. So we're going to go resistance varies directly with the length, so k L, and inversely as the square of the diameter. Okay, so this is what we call a combined variation, because what we have in a singular problem is a direct variation and an inverse variation. But all I've written to this point is the direct variation. So if you can think about it, think about what an inverse variation would look like. It's xy equals k. Well, I already have y equals kx. What if I were just to ignore this L right here and say that wasn't there and I wanted to write my inverse. It's the square of the diameter. So to write that, I'd say d squared, but then I just previously had a length right here. So this is my direct variation here combined with my inverse variation up here. So once again, that's called combined variation. And it looks like they're going to give us a couple situations. We have 100 meters of wire. We have diameter of 6 and a resistance. Then we have 80 meters of the second wire and a resistance of the second wire, and we have to find diameter. So again, I would set this up in a proportional fashion. I would say d squared r over L, which is equal to K, and that's my case 1, is equal to d squared r over L in case 2. So I'll go ahead and do that. I have my first case of a diameter of 6, so that's 6 squared, a resistance of 6, and a length of 100. And that's going to be equal to, we're looking for the diameter, we have a resistance of 15, and we have a length of 80. So this is once again going to be a calculator problem. I take 80 times 6 squared times 6, put that over 100 times 15, and I'll have to take the square root of that when I'm done. And that will give me approximately, if I go to the 100th, 3.39 millimeters. And now we know H is jointly proportional to the square of L and W, which means there's joint variation. So H equals K times the product of L and W. And we want to find the variation constant. They give us the L value of 2, the W value of 1/3. Don't know K, but we know H is 36. So if I want K, I take 36, divide by 2, multiply by 3, because that's like dividing by 1/3. And there we have it. So that's basically just going to be 18 times 3, or 54. Let's just do one more. The volume varies jointly. So here's volume equals K as the height and the square of the radius. So that's r squared. And again, we're just going to find the variation. So the cone has a height of 8, diameter of 9, which means my radius is 4.5 squared, and the volume of 54. So I'll just take 54, divide that by 8, multiplied by 4.5 squared, pop that into a calculator and get an approximation. It ends up being exactly 1/3 for K. And that's all we've got for you today. Make sure you do your Connect Ed, fill out your survey, and we'll discuss more tomorrow.